Okay, it's time to discuss the incentive that atoms feel for chemical bonding. It's time to discuss why one atom feels the need to bond to another. We've discussed this a little bit so far, and we've decided that valence electrons, those outermost electrons, they are the ones that are primarily responsible for the way that an atom behaves. Let's look a little bit more closely at these electrons, how many we have and where they'll be. So we know, just by looking at our periodic table, how many electrons an atom has. So I've got a silicon element there on the display for you, and you can see it's element number 14, so we know it will have 14 electrons in total. But how do we know where they are and which ones are the valence electrons? Let's start by having a look at how many electrons we can fit in around an atom. So here I have a different diagram of an atom. We've got a nucleus in the middle, and each of the spheres that surrounds it, they are the different shells I've been talking about, where those electrons will reside. They're not actually two-dimensional circles like this, but it's the easiest way I can represent it on a diagram for you. So we've got these shells, just the first shell, second shell, third shell, fourth shell as we're going out. There is a simple equation we can use to determine how many electrons can fit into each of those shells. That equation is up the top there for you. It's 2n squared, where n is the shell number that we're talking about. So for example, if I'm in the first shell, n equals 1. 1 squared, 1 times 1 is just 1, and then times 2, that's 2. So in that first shell, I can fit 2 electrons. If we move out to the second shell, 2 squared is 4, times 2, that's 8. Third shell, try the maths for yourself. I'm hoping you end up with 18. And the fourth one together, just to make sure we got the right of it, if you're in the fourth shell, 4 squared, 4 times 4, that's 16. Double it, times 2, and that gives you 32. So we can very easily see how many electrons we can fit, maximum, into each of these different shells that surround our nucleus of the atom. But that's not precisely what we're after. What we want to know is how many valence electrons that we will have for any given atom. Your periodic table makes this challenge much, much easier. You remember that your periodic table is arranged in groups, and we discussed the group numbers across the top, and that focusing on the highlighted groups, we were going to number them 1 through 8 across the top using those Roman numerals. If you're okay with this system, it makes your life much, much easier. Why? Because the group number directly relates to the number of valence electrons that each of these atoms have. So I've now got a periodic table there for you, where I'm using a little black circle to show you how many valence electrons each of these atoms originally has. If you look at all of the elements in group 1, all of the alkali metals, they all have 1 valence electron. Pick another group, all of the elements in group 6 in orange, they all have 6 valence electrons. So again, very easy to immediately tell how many valence electrons any of these coloured elements have just by looking at the group number that they're in. So far so good? Right, I now want to talk about the ultimate goal of these atoms. We can see that group 1 has 1 valence electron, group 7 has 7 valence electrons. I want to talk about group 8. These all have 8 valence electrons. We've talked about this group before. We called them the noble gases, and I said they had another name too. That other name is they are called the inert gases. Inert means that they don't react. These chemicals, these atoms, form very, very few compounds. It's very difficult to get them to form bonds. And the reason for that is they are completely happy with their electrons just the way they are. They don't want to share or give or take. They don't want any changes at all. So these noble gases, these inert gases, they have the ideal electron configuration. They are happy. All of the other elements in the periodic table are jealous. They want to be like these noble gases. They want to have that same electron configuration. How do they achieve that? They bond with one another in order to, however they can, match that electron configuration. So what's special about that electron configuration? What it is about them? They all have, with the exception of helium up the top, we'll talk about that shortly, all of the others have what we call a stable octet. They all have 8 valence electrons. This is a particularly stable state for the atoms. All the others will strive to reach this. They will strive to get there by bonding. Yeah? There are a few exceptions to some of the things that you and I have discussed in our periodic table. For example, if I move to the middle of the periodic table, these elements are a little bit more complicated when it comes to predicting the number of valence electrons that they have. They can be a little bit variable. It's not going to hold us back from forming compounds with them, but it does mean I won't ask you to predict how many valence electrons they start with. We really are going to focus on these elements here, in which case I'd like you to be able to simply look at the group number and say, that one's one of the aqua ones in group 3, that means it has 3 valence electrons. I want it to be that simple. If that's the case, they are all trying to get that stable octet. The one exception that you and I are going to discuss in our periodic table, there are some atoms that aren't after that octet. Some atoms, particularly some of the large ones, can actually take on more than 8 electrons. They'll be quite happy that way. We won't worry about those exceptions. The one I want to talk about, the small atoms, the first 2 or 3 atoms. If you remember earlier on, we discussed how many electrons fit into each shell. In that first shell, you can only fit 2 electrons maximum. That's the total. So if we look at helium, that first noble gas, the first one that's completely happy, it only has 2 valence electrons, and yet it's completely happy that way. Other small atoms, like lithium and hydrogen in particular, I really want to emphasize hydrogen, that is a common exception. It will be perfectly happy with 2 valence electrons. But for all of the other atoms that we've been discussing, all of these colored atoms I have on this periodic table for you now, they all really want that stable octet, 8 valence electrons. They're going to get that by chemical bonding. We'll talk about how those bonds form in the next topic.